So let's continue our enhancement in spatial domain. I think today we are going to finish this. There are three Gaussian. Yeah. The third one is by when by yourself. It's not difficult. We only write some fundamental techniques for. So let me remind you this one medium filter. Actually, this linear filter is value of mask. Part of your mask you are going to compare. So by 3, 5 by 5. So later, later number, 9 number to choose one. So it's right. But however, if you use some even mask, so you are going to choose you are 4. There are 4 by 2 mask. Here. Second number. So it's depend on your mask. So it's even or 3 by 3 is a 9 pixel. Medium. Okay. So why we do that one? Because I mentioned sometimes your noise, is not like Gaussian. They are not beauty in your mask. Sometimes it's some inverse noise, first like okay, some bottom paper. Oh no, paper noise. So like the white spot. So sometimes you look at it, white spot or black spot. You your great image. However, this nonlinear type mask filtering will do a much better job than linear filter. And we also have type of different nonlinear filter. Maybe number and the minimum filter is number. For example, you have so you image located on here. So you pick up all the neighboring pixel and all the number from your image gray label, and then use a maximum replace to this center. And however, can you tell me if you use mass data, what kind of noise you use mass data? What kind of noise will be? Oh, okay. So there are some white spot, red spot. Here's a file mixed with filter. We call it what kind of noise will be different. White spot or red spot. Should be red spot, right? Red spot in the label is a 0, right? Right. So noise is 255, like 255. So if you use mix, so you are graded by a red spot, it's 0 there. So it will disappear. It will be replaced by the neighboring, right? So the low value, no spike noise will here. filter, the white noise, the white spot noise will, because you use minimum request, the neighboring minimum request that beautify, right? So the white spot will display immediately, right? So you look at the image, and you know your image is degraded by the white spot or red spot. You can choose maximum filter or minimum filter. Restore your image immediately. However, if you have a white red spot simultaneously appear on your image, you have to use a maximum plus minimum or minimum plus maximum. Continue to make filter to solve this problem. For sure, you can use median at a time and solve this to spike noise immediately. Okay, at the same time. So median is nonlinear. So sometimes we have a maximum filter, we have a minimum filter. So it should be very easy. And then after ordering, which one you are going to replace your original pixel value. Use median value or maximum value or minimum value. But because it's a nonlinear, so you cannot say this one equal to max plus minimum because the result will be totally different. Nonlinear, you never know the result. So what happens to each other? They are different. So you apply minimum first and then maximum first later. The result will be different. Max first, minimum later. That's nonlinear. Everything will be replaced during the process. Okay. Okay, so it's a nonlinear field. Okay. So depend on your degraded image. So which kind of nonlinear filter you are going to apply? It's very easy. So median is just give the mask and then all the gray value appear on this mask, and then ordering and pick up the center. Okay, pick up center to replace your original intensity level, and in that case, some nonlinear noise, spike noise will be removed immediately. Okay, so let's compare. Okay, so there's an example for the noise reduction. So we mentioned in previous we use a low pass filter, Gaussian filter. Gaussian filter is a low pass filter, one type of low pass filter, linear low pass filter. So every different added noise value, but distribution as a Gaussian level. So this is the result for Gaussian noise degraded image. This is for salt and pepper noise. Salt and pepper noise, so white spot, black spot noise, with probability of 0.2. What's the probability of 0.2 means? Which means it's very highly degraded image. Every 10 pixels, there are 2 pixels will be degraded, will be add one bright break or one white spot. Okay, the probability is very high. So it's noisy image. Okay, so your paper, salt and pepper noise, how you define it? You define probability. 0.2 is very high percentage, 20% of the noise appear in 100 pixels. There are 20 pixels added with spike noise. So very noisy image. And this is the Gaussian noise. So you know Gaussian, you have to assign the K, Gaussian K exponential to sigma squared R squared. Okay, so you have to define K and sigma. So here sigma is 0.2, K must be 1 for the Gaussian noise. So you see there are some noise image at your hand. So how can you do it? So actually, if you look at carefully, there's some spike here, but this one is more smoothing noise on this image. So, but let's try. Let's try to use different filter, linear filter or nonlinear filter to solve these two images. And how you compare? How you compare your result? Which one is better for the resulting image? signal to noise ratio. So you use signal noise ratio, this kind of measurement indicator, to see exactly the result, good or bad, which one is better. So how you do that one? The unit is a decibel. We call it dB. Decibel, how many decibel? And how you do that? It's SNR. SNR equal to power of signal. Signal compared to power of noise. Or amplitude of power squared. Your amplitude compared to amplitude square of the noise. Okay, so this is the major conception for measure your noise iterated result. Is that good or not after you do your enhancement or restoration operators? So let's see. So how you calculate? So you can write a very simple program for that one. Power signal is power signal. It just sum up all the square of your intensity level. So it should be like this one, summation from maybe x. We use x one to your image size, and y from 1 to your image height, width and height number, and then your image pixel, take a square. So it's a power of your signal. Okay, so you have 256 by 256. Every pixel head is a gray label. So you take the square and then sum up all these pixel square of the pixel intensity level, sum up together. So how about the noise? Medium filter. After that, you remove the noise. So you have the image without the noise. Okay, so power of noise will be equal to the same. You have to add up all the noise and noise power. So we write up like this one, summation, also from 1 to m, y from 1 to n. And what's this? It's f of xy minus f of hat xy squared. So what's that? F hat is after you remove the noise. You use a Gaussian filter, median filter, maximum filter, minimum filter, average filter, low pass filter, and then this is your estimate result, and this is noisy with noisy image. And a difference in every pixel. And the difference is supposed to be right, that noise there. So your original power divided by the noise power. So the higher is better because the difference. So that's the way we do that one. However, you are going to use decibel as your unit. So you take a 10 log, take a log and then times 10. So this one is you can do that one. So it's like 10 log base of 10 power of signal, power of noise. We just calculate power of signal, power of noise. So this is the way you do this SNR, signal to noise ratio. So it's a common way to measure how was your image remove the noise and what's the SNR left. Higher is better. So we compare these two values to other techniques. Okay, so if you want to actually how do you use the amplitude of that one? So that's fine. You just take a, because amplitude is take a square of amplitude become power. So if you use amplitude, easy. Decibel unit. So you can compare the one. Okay, so it's a way to compare how was your performance of your filter. So let's now we compare the mean square error. So actually this is the mean square error as well. The noise is a mean square error. What's the error you can find out. So a mean square error also less mean square error is better. Okay, the same as your SNR. because your denominator smaller, your SNR will be larger. Okay, the same idea. So let's see. When you add up this noise to this image, because you know your original camera main image result noise, so you can calculate mean square error. So take the original and additive noise together, and so you have a noise and take a square from each pixel value, the differences, and then take the root mean square. So its average is 0.0337. For the spike noise added degraded image, the mean square error is 0.062. So you can see they have different mean square error. Okay, use different type of noise, edited noise. And then if we use averaging filter on both Gaussian degraded image and spike noise degraded image together, so use linear filter on both image. And what's the result? So you can see it's improved, right? Mean square error decrease. So decrease from 0.30337 to 0.0075. So decrease a lot, which means I use some Gaussian filter, average filter, to remove the Gaussian noise, because Gaussian noise is some type of Gaussian noise, and it's good to use some average filter. Quite Gaussian noise, if you use average filter will be good. And distribution, like noise, like this one, right? So it's a 0 in the center. So if you think about it, when you have a big mesh to remove all the image, and your Gaussian active noise is a Gaussian format distributed -5. So you average the noise will cancel out, right? So when you take the average, the noise will cancel out. So it's good for the Gaussian noise, degraded image. It's good for use average filter, because average then the Gaussian noise will be removed. So you can see the result immediately improve. The MSE decreased from 0.0337 to 0.0075. But if I use average filter on white noise degraded image, so actually the results also could improve. But compared to the Gaussian, they didn't perform so well, because the Gaussian noise is not good for nonlinear filter. However, if you compare, we use medium filter to solve this problem, to enhance the degraded image by Gaussian noise, nonlinear filter, and the spike noise. So you can see this one compared to this one, not good, but also improve. It always can improve. Your low-pass filter can improve your active noise, but the performance is not as good as use averaging filter. Okay? So 003/3 is the same. However, for the cameraman degraded by the spike noise, their MSE compared to the average filter, the nonlinear filter, much better, because that image was degraded by spike noise. It's good for medium filter. Use medium filter, so you can compare. Okay. Rated by the active noise. The active noise, the spike noise. So think about nonlinear filter. Okay? Nonlinear filter gives better performance compared to average mesh of S filter. If your image is graded by Gaussian light noise, okay, and use some average filter will provide a better performance. So this one is better than this one. Okay, so that's conclusion for this noise reduction. So we use some low pass filter or use nonlinear filter to remove your additive noise. Additive noise. Everywhere you can have additive noise through your image acquisition, image processing, image transmission. You have a lot of different process. They always have some additive from the devices. So you have to understand how to use them. If you know the noise characteristics, it will be easier for you to choose the right filter. Okay, so here's another example. Here is the X-ray. Left one is X-ray image of a circuit board corrupted by a salt and pepper noise. Again, so when you look at this one, so the first thing you have to make the right decision. What kind of filter I'm going to remove the additive noise? So it's a spike noise there. Sometimes it's a white spot. Sometimes it's a black spot. So I know a better choice will be the nonlinear filter. Okay. So unfortunately, if you choose this one, B is a noise reduction using a Gaussian 19 by 19 Gaussian filter, low-pass filter, with a kernel of a sigma equal to 3. Again, if you set up sigma equal to 3, what's the mask you are going to design? What's the size of the mask? Just mention in that. You have a Gaussian filter design, you are going to input the parameter of the sigma. You find this mask and say, what's the sigma you are going to use? If I say I'm going to use sigma, means your filter, your best Gaussian filter size will be 19 by 19 because 3 sigma equal to 3 times 6 times 18, right? 18 is not good because it's a number. So 19 will be good for this Gaussian. So your mask will automatically design to 19 by 19 and put the Gaussian value coefficient into this number. Is that okay? So here we'll extend your result. Not always use 3 by 3 Gaussian noise because the Gaussian low-pass filter because it's too small. They cannot see the Gaussian shape of your filter. Okay, so if you use sigma equal to 3, so your mask will become 19 by 19 mask. Okay. 6 sigma by 6 sigma. Your mask size, your N5 should be like this. And then use this Gaussian equation. So we also ask what's the K, what's the sigma you are going to design because your Gaussian filter of XY. Not use G. Filter 1, okay. Filter Gaussian XY equal to K exponential 2 sigma square R square. Actually, R square is X square plus Y square. Okay. So we'll know the K defined, sigma defined, and the input parameter, sigma and K. And I know your mask will be times sigma as your input mask. Okay. Okay, so let's see. This is a use Gaussian filter on this spike noise active result. Is that good? Definitely, it's not as good as your imagination. So we know it looks like spike noise, but we try to use a linear Gaussian low-pass filter, but the result is not good. No. Okay, that's a characteristic of the noise. However, if we choose the C is we use a noise reduction, use 7 by 7 median. So your homework is also have a 7 median filter. So we will ask you what's the size. So you have to give the size. Input parameter. What's the mask size? Why? But have 7, you will be give a 7 by 7 mask. 7 by 7, and then you are going to order all this 49 number in your center pixel and see the neighboring pixel, and then order 81 and take the median will be what? 25th. The ranking at 25th will be your output to replace the original pixel value. And this is the result. Okay, so compared to the Gaussian. So definitely this one, the mean square error will be lower than the left one. And in other words, the right SNR will be much higher than the left SNR. Actually, if you look at some of the SNR, there's another terminology for like a peak with this kind of nonlinear evaluation. We call it more SNR. Okay, especially for this kind of some peak noise there. So we call it a peak SNR here. Okay, how you define that one? Actually, this is the similar to our original, but we don't look at the intensity level of the image content. We always use peak number of the intensity replace the original signal. So it becomes 10 log of the maxima square and the mean square error here. To show your performance. So for the 8-bit image, and it should become 10 log of 255 square divided by what? Divided by mean square error. The same mean square error. So it's your image minus your removed image square. Take the value of, so you take every pixel minus you remove what we consider as a noise level. So this is called SNR, signal to noise level. So two of these indicators. SNR or PSNR. Okay. So are you okay? So these two kind of indicators you'll see a lot on some software. Okay. So this is a low pass average filter for your image graded by some active noise, and you will see what kind of noise you are going to remove, and then the result you use SNR or PSNR to compare their performance. Okay, so now let's jump to another area for the image enhancement. We call it high pass filter. Okay, so previous is kind of remove noise, so low pass will work. Now we are going to sharpen our image to see the high frequency part, because we mentioned your image contains some low frequency band and high frequency band. And the edge information, some edge information will always locate in a high frequency band. So in that sense, if I want to enhance the edge information, so I have to perform some high pass filtering idea. Okay. Okay. So now we are going to talk about high pass. Most of high pass is based on derivative. In calculus, we do some derivative, right? So it can be a highlight sharpening your spatial domain, and so we use them like first or second order derivative. So in the calculus, use a relation. So we have a one first order, take a derivative one time, or the second time, or the second order derivative. Okay, so let's look at this image. How we do this one. So here's the image. Please look at the white spot here. Okay, here, white spot here. So if we take a cross line from this one and cross through this white spot. Okay, I didn't do a good job here. So if we pass through this white spot, take a profile. Look at the grade level distribution of this image at this line, cross line. What's the result? You can imagine the white color will be high grade level value. The black will be very low grade level value. All black is 0. All white is 255, right? Depending on your bit. How many bits to represent 1 pixel? So if it's 8 bits, so the range will become from 0 to 255. If it's only 3 bits, the grade level will become from 0 to 7. Okay, depending on your grade level. However, if you look at this image, this is kind of shaded white, shaded to slowly to black. And then there's a spot, black spot here. So there's a spike point, because white is the highest grade level in the image. So the white spot. And then you have a line, cross line, from black to line segment. And then from line segment to background, black. And then there's a step function from black to white. So can you imagine the profile of your intensity level should be like this one. So corresponding the cross line, and then you look at the grade level distribution, will be look like this one. So it's a ramp function. This one we call ramp function. Ramp function. It's a ramp. Okay. Decrease linear or increase linear is a ramp function. And then this one you call it isolated point here, white spot. Oh yeah, here is the name here, isolated point. And this is a ramp function. And here is the background, black color here. Okay, black color, so it's black color, and isolated point, black color. And then there's a line section here, line. So it's also increasing slowly to the gray color. And then because it's some range, so it's triangle shape like the thin line, very thin line, not thick line. And then there's step function there. So it's black color here, and then jump to white color for all the way to the border. So it's a step function here. Ramp function, isolated point, and then a flat segment, and then thin line, and then step function. So if you take a profile in this profile in 1 dimension, right? But for the two dimension, you look at this image like this. So how you do that one? Now we are going to enhance, right? Sharpen this image. How do you do that? Where is the important feature you would like to look at? Okay, so this is not talking about the noise, additive noise. We are talking to enhance your image, sharpening your image. So in this mathematics, we always use a derivative. Actually, derivative in calculus, in discrete signal, we call it differences. Derivative. And in image processing, how you achieve this derivative? Actually, you just take the differences. Take the difference between the neighboring pixel, the value of the neighboring pixel. You will see the difference between them. Okay, so let's see. Derivative in mathematics, we say it's a wrong. But it's 2 dimensions, so we have 2 parameters, x and y, in 2 directions. So for df dx, how we write? It's f of x plus 1, the next one minus f of x. So it's a 1 order derivative, right? And in image, how do you do that one? How do you achieve this derivative operation? Actually, just take the next neighboring derivative label minus the f of x, the pixel you are going to look at. So how about the second derivative? Okay, it depends on your how defined in the first order derivative. So maybe we add one more pixel, one more page. So we say run f run x equal to f of x plus 1 minus f of x, right? How about the second derivative? So do it twice, right? So it's run x, sorry, x. And then this is the f of result for this one minus f of x plus 1 minus the is f of x plus 1 minus f of x. So what's the minus twice? So the result will be like this. Minus the result like a next pixel. So if you look at the f of x, so it's a minus 2 f of x plus the 2 neighboring in your neighbor. Okay, so it's similar way to describe. You do derivative twice at this location. So the result is minus 2 of your location intensity label times twice times minus 2 and plus your previous one next and the next neighboring value. So let's go back to look at our image here. Okay, so we take a profile on this for example 9 of this specific point close this spike white spot, and then the result like this. So you can see 5 rand value 4 3 2 1. So it's a 3-bit. Take an example. This is a 3-bit, and then for the isolate point, the highest value here 6, and then background, and then the C9 1 3 1, and then step to function to 7 7. So if you take a close profile and you get this 9 intensity value at this profile, this cross section. So you are going to do first derivative. So what do you do? So the result will be replaced by what? The next pixel minus myself. Next pixel minus myself, and then put into the result. So next pixel minus myself become minus 1. So put here. Definitely you can write a 0 here because next pixel minus 1 here. So every pixel in the next value minus itself. So result like this one. So in this range function 0 1, so it's minus 1. The background 0 0 will be this one. The isolate point will be 6 minus this 0, so it's a 6. And the next one will be minus 6, and then the background the same. And then this is the thin line. So next pixel minus 1 minus current pixel. Next pixel minus this one. So you can see when your intensity level increasing, your slope is positive. When your intensity level is decreasing, your slope will be negative. So you only look at the value of your first derivative result. You know what's the intensity level trend. It's going up, going down. And this one is like this one step function become 0 to positive. And next pixel, the derivative will become 0 because it's all white background. So the difference becomes 0. So you can see at the border, they have some value exist. But for the rim, their slope is consistently like a small value there. So it's the first derivative result. How about the second derivative? We say you just multiply your cell location twice, negative 2. Multiply this factor, negative 2. And then plus previous one and next pixel. So here, this one times minus 2 is become minus 10 plus 5 plus 4 becomes minus 1, right? So every pixel you can calculate. And this one is minus 2 times 0 plus 1 plus 0, so it becomes 1. And every pixel here, you just minus 12 plus 0 and 0 become minus 12. This one minus 0 plus 6 and the 0 and 6. So every pixel here, you know the second derivative value, the result. For this step function, see this one is minus 2 times 0 plus 0, 7 become 7. And this value minus 14 plus 0 plus 7 become minus 7. And this value minus 14 plus 7 becomes 0. So they are very interesting phenomena in this result. For a second derivative, you can measure the step function immediately. Why? So different type shape function, you can have different result once you provide first derivative or second derivative. For this one, you have a very good zero crossing point occur. So you have this kind of step function from 7 to minus 7. Okay, so we call it crossing point. Crossing point for, and also we call it double response. Okay, sometimes we call it double response for this step function. Double response here. Okay, so it's I think it's quite easy. Okay, straightforward. First derivative and second derivative, you can see how the profile provides you a suitable information to detect. So it's just easy take the differences between your neighboring pixel. Here is another example for the value scan line. Again, so you can see there's no spike noise. So again, if you look at this one, and you know they will have a step function there for the second derivative, and there's some change, slope change, and then yeah. So I just give you another example. I think it's quite straightforward. So nothing special. As long as you know, sometimes if you look at the zero crossing point here, okay, zero crossing here. So the black spot is first derivative. The rectangle is for second derivative. So you can see how the second derivative change. Especially for the step function, there's some zero crossing value there. Okay, from positive 5 to negative 5. So that's the way you have to check out second derivative. So how can we use this kind of difference information in our image processing and to sharpen your image in a good way? So now we are going to introduce image sharpening, very important enhancement techniques. Especially if you want to look at the detail of your image and how to do some a good way, combination good way to reveal, to show your image in a better vision, to involve the highlighting fine detail. So that's the way to enhance the low detail of your image. And then it's have been blurred. So the high-pass spatial filtering is a technical difference. So if you look at your image filtering, if you look at the mask, actually you have the idea what kind of operator you are going to perform. For the averaging filter, if you think back, the averaging filter for the box filter is 3 by 3. All the coefficient will be positive. 1 divided by 9, 1 divided by 9. Every coefficient of the mask positive. If you look at the Gaussian filter for low-pass filter, again, it's the coefficient all positive there, right? All the same signal there. However, if your mask including some positive number, some negative number, as some kind of a difference operation or derivative operation in the filtering. So, which means you are going to take some high pass information, high pass band information from your image. So, basic high pass spatial filtering can be accompanied by linear shifting invariant operator implemented by the mean of a mask with positive or negative coefficient. Let's just mention, if you have positive, negative, because they are going to do some derivative difference operation, and the mean should be 0, because you are not going to increase some extra variable. However, if your mask, later we are going to do some unsharp mask operation, so the total will be larger than 1 or less than 1. So how can you do? You are going to do normalization at your output, because your summation result should not be more than 255 for the 8-bit image, right? So sometimes you have to protect your image output. So do some normalization, transform from your input image, the result image, to a range of 0 to 255. Okay, if your result has some value larger than 255, it cannot be shown, so you have to do some protection. Okay, so it's called sharpening mask because you have positive, negative noise coefficient. You are going to do some enhancement there. So since it tends to enhance a lot grayscale change in the image. So if you go back to see, only the aging pixel will be enhanced, will be some value left. Otherwise, if your constant background, constant foreground, constant object number, your difference will be 0, right? So only edge component will be enhanced, will be left after your high-pass spatial filtering, right? Okay, so for the constant gray label, the difference will be 0, nothing there. So we are going to do some performance again. So it's kind of mask. So because add up is 1 layer, 0 layer, so it's okay. The center negative. Also, you can perform negative here, positive outside. It's the same. The same difference filter layer. Okay, so it's called a high pass filter in there, and the high pass filter image G also can be done through the combined with the low pass filter. So previously we know low pass filter, right? You know the averaging filter, box filter, Gaussian filter. It's fine. So in frequency domain, it's very easy to expand. So it's a low pass filter. So if this is 1, it's a low pass filter in this band, or in frequency, we say omega. So now we need to do some high pass filtering. So I'm going to remove out the low pass filter. So this is a low pass filter. So how about high pass filter? How to do high pass filter? Actually, you just take a constant 1, and then minus this original low pass filter. So you will get this one, right? So it's a constant 1 here. So take a constant and your frequency domain minus your low pass filtering design, and this is high pass filter. So only signal with the band, with the frequency component higher than B, band B, frequency B, and then will be left. And this is low pass filter. So how do you do that one? Actually, you just take the difference between the image and the low pass filtering. So the most easy way for you now is just apply low pass filter first and original signal minus low pass filter result. you get what? High-pass component. That's it. Okay, very straightforward. So your output H information, what do? It's a original image minus you apply box filter, Gaussian filter, and you get a high frequency component. But this is some example just that you know. Later on, we are going to introduce more complicated design, not this straightforward one. So you see, this is a original image. This is a high-pass filter result. How do you do that? Just use previous image, use the average filter, and then use original image minus your low-pass filter result. You get the H information differences. Okay. So we'll take 10 minutes left. Later on, we are going to introduce some Hypos, your third M file. You are going to design. It's a very useful one. Why? So if you look at, if you use Photoshop, this is a kind of result. But it's very complicated because there are three very important parameters to design. Can you see the differences? Can you see the differences? Before, right? So use the link you see on your telephone. You will see much clearer than this one. Are you serious? You cannot see the differences? It's original image. Vector type boost, but look very nature. But look at detail. Okay. How intense that one? How intense that one? So that's your homework. Type boost. Okay, we try to enhance the high frequency component without sacrifice your low-pass take means that rest.没有一定要忽略，学写课本没写我也没写，当然还是要，但是你要你就是 border，因为它剪不到前面那个。这边要 pending。对 pending，只有 pending。你要 pending，按种 pending 我怎么知道？你可能会 mirror， 对不对？你可能会反过来，你可能会 constant， 你可能会忘记。就 depend on you。OK，bordering，OK， 就这样。然后我想问对。那我们在做的时候，我们要怎么去验证说我们做完了？他没有办法，我已经开始讲了。这个 enhancement 没有办法，那只能用眼睛，然后用7个方法，7个非常好，普通好，不错，这样。对，要人来。可是像我肉眼根本看不出来说。哦，真的吗？对，细节上差。真的吗？哦天哪，你不要开玩笑哦，来，就看这里好了。有没有比较 sharp？ 有没有？你看不出来吗？看不出来吗？绿色。眼睛好了，很 bright。你看，模糊的。你怎么会看不出来？真的看不出来哦。你看图像这种东西，没有那么敏感。你看出来吗？可以了哈。而且它保持很自然的。对。不是像那种加上去以后，哇，那等一下我们会看了。好。你如果弄错的话，会，这没有人跟你讲答案，你要自己 try 那个。影像是什么不知道。影像是什么不知道，但是这是非常明显差。你看这个亮。这个亮的那个对比，鲜艳度跟清澈度比这个好多了，好不好？好，因为这是 Photoshop 的那个了，我不能给。an example。
some students ask me how to measure the quality of this 2 image. For the noise removing, we know we have a signal to noise ratio, right? SNR, you see there's a pair between 2 images. But for the high pass, there's no standard criteria based on subjects who are viewing these 2 images. Which one is better? Okay, so if we put a block here, very clear detail, right? Here you look at this eyes, the blur, but it's very clear, right? Very small pixel, very clear. So maybe you will think about this is a better image, enhanced image. But if you change the person face, okay, then will be better because your pinpoint, everything will be not also clear, right? So image enhancement, sorry, there's no standard criteria. It depends on viewers, subject. So you have both. We have 7 different criteria, and very good, good, little bit good, no change, that's the same, a little bit bad, a little bit big, worse, and then worse. So there are 7 different reports, and it depends on the result. Okay, so it really depends on who review this image here. So let's see. How can we do this one? We call it high boost filtering. So this is the filter mesh used to implement this Laplacian. Okay, so here's the Laplacian second order derivative result for the high pass filtering. We call it isotropic derivative. Because remember, we just mentioned one dimension. What's the one dimension? One dimension result is a rho square f rho x, right? So it's fx plus 1 minus twice fx plus fx minus 1, right? So you can see the coefficient here is 1 minus 2, 1 here. For the horizontal derivative, second order derivative, right? So how about the vertical? How about the vertical to y? Okay, this is xy here, but now we are talking about vertical edge difference. So you do vertical, you will see horizontal edge. When you do horizontal, you will see vertical edge. Okay, different direction, right? So it's the same. So it's become right similar mathematics. So here, if you respect to y direction, you will see the horizontal edge. If you respect to x direction, you will see vertical edge. So if you combine for the 2-dimensional, you combine these 2 together, what's the result? What's the result? You are doing it horizontal, vertical at the same time, so you have this one. Right? To be like this one, right? Okay, so it's for two direction. And now you are going to ask me, how about the 45 degree, 135 degree? How about the 135 degree and the negative 45 degree? So, which means you have consider this one, the edge for the diagonal edge. So we add up this one, and then it's become minus 8 here. Both isotropic direction, you are all going to take good care of it. So you do it at the same time. So we call it an isotropic derivative, like this one. Isotropic derivative. And you can use positive content or negative in center variable because you're just doing some differences. So you can use neighbor to minus u, the current pixel, or you use current pixel to minus neighbor. So who is the center is fine. So similarly, you can do this one with edge, but it becomes negative 1, your current pixel minus your neighboring to see the differences, right? Okay. So both, we call it Laplacian filter here. So we give a name, Laplacian, second derivative, Laplacian filter. So if I'm going to ask you to design Laplacian filter in all directions, we call it isotropic derivative. ISO, isotropic derivative operator. This kind of kernel, isotropic, in every direction, the same. I'm going to take care of it. So this will be like this filtering. Okay, if you want to include diagonal neighbor, okay, and two other information. So this will be very common Laplacian filter in your some software package. So if you look at Laplacian here, Laplacian, so you know it's a second order derivative. Okay, is it okay? Yeah. So now we are going to introduce another one. We call it a high boost filter. Okay, it's a little bit complicated, but the same idea. Okay, how do you do? This is a filter whose output is produced by subtracting a low-pass Berfield filter and then of the F from the amplified version of F. We just mentioned. You want to look at the order of your image. Very easy. Use high pass minus low pass. That's it, right? Only what? Only edge border left. Remember the example here? This is the original image minus low pass filter. Right? Very easy. Your original image, take a low pass filter, smooth, and then take the differences. What's the result? If you look at this one, what's the result? Only edge information, right? But if I present this picture to you, you'll see it's ugly, nothing good, because you don't have the original content there. You only have the different content there, right? So how do you do? Add back the original part of it, right? So add part of your original signal, or use weighted signal to your original image. So it's just part of your want to enhance component, but it's not your original image. So what do? You can do is add back part of your original image. So A here is larger than 1, should be, because A is maybe 2. If A equal to 2, what's the result? Is that clear now? Is that clear now? A is larger than 1, which means if I A decompose, if A equal to 2. Okay, so it's a 1 plus 1. So I separate these two separately. F plus 1, F plus F, right? 2F, right? A equal to 2. So the second F minus low pass filter. So what's the result? High pass filter. And we just show you the high pass filter result. Only F information ugly. I add back your original image back. Very straightforward result, right? So it's called high boost. Sometimes we call it unsharp mask. In Photoshop package, they call it unsharp masking filter. So maybe you cannot find a high boost, but you can find an unsharp mask filter, but different coefficients there. So is that okay? It's original low pass filter, and then use larger weighted original image add together back. Or you can say this is plus high pass filter of F. Okay, so actually for the high boost is focus on this one. You can enhance more high boost content with some constant there. So you can have a weighted high pass band component. It depends on you, depends on your image. So you just see the plot result. Actually, you can do tuning 3 different parameters to get the best result. You look at it, satisfy your expectation. So here is just some process, okay, mathematic process to see what's the result there. So you can see I can separate A minus 1 and plus 1. So it's the original A plus A times F, and then just what I described. If A equal to 2, it becomes F plus high-pass filter result, right? So high-pass filter or some weighted high-pass component to this result. A must be larger than 1. So because I extract original image here, and then to minus low pass to get the high pass result. So it's the result just like this. So let's look at original example we mentioned in previous one for the high pass filtering, right? So that is original image. So we have the high pass filter, and then get this only edge component. But now we are going to add back original image, and the result becomes like this. So it's maintained original image, but the border of the image is highly boosted. So contain the original information, and the edge is much clearer. So see inside there. So the border information will be added back to that one. And how we do this one? Actually, there are some standard process for the unsharp mask filtering. Unsharp. So in that one, we call it unsharp mask. Okay, so there are 3 steps. The first one is blur image. Step 1, blur image. Okay, so the unsharp mask they're doing, this one is unsharp. Blur your original image first. So we call this F bar. Okay, bar is average, right? So for example, you use F bar filter, you just average your original filter, get this one. And the second step is subtract your blur image from original. The next image equal to what? So original image minus blurred image. Okay, so the third one is A, weighted mask. The G mask to the original. So that's the way you are going to write your third M file. Okay, so if we write in mathematics, we'll see G mask equal to this one, right? So your final image, G image, not control. Okay, G image, your final output, unsharp or high-pass filter is original image plus weighted number of image. So this is a main idea for the unsharp mask filter or high-pass filter. First, for your image. Second, get the mask image. And third step, add back, multiply some weightage coefficient of your high-pass result back to your original image. So if we write it mathematically, we have F plus K mask is a K times F minus F bar, right? So equal to K plus 1 F minus K F bar. Actually, similar to our previous one. plus 1 is like our A coefficient. Then A must be greater than 1. So K is your choice. K is your parameter. You can choose K equal to 1, and it becomes twice of F original image minus average image. Okay? So here we say K can equal to 1, 2, 3, blah, blah, blah. And if we set up K equal to 1, actually this is a short mask. You want to compare them? There's still a little bit differences. So G output is equal to 2F minus F. Hypothesis. Actually, they talk this together. Okay, they didn't state this. Separate these two applications. But anyway, just see. Actually, we are sharpening this image, right? But we are not only sharpening. We have to come back, add back the original image for your image. Actually, for the Photoshop, how they do this one? For Photoshop, actually their design is like this one. I can check out their brochure. How they did this one? They design like this. And now you know the sharp mechanism. You can totally understand how they design these ones in a very detailed way, and a good result for you to compare. Okay, similar. So in the Photoshop, the image input goes through Lopez filter, and then multiply some coefficient here. Also, the image multiply another coefficient. So if you add it together, they will become 1. Part of your image, part of the coefficient, weighted your Lopez filter. Part of the supplementary coefficient times to your original image, and then add it together. So your output is like this one. Your output is equal to what? Some coefficient, weighted coefficient for your original one, and then minus these coefficients, they add up as 1, right? And times your Lopez filter result. So it's also hypothesis. Idea. So your Lopez filter and high-pass component, and then add back some your part of your original image. So it's a sharpening amount. The second one is sharpening radius. The third one is a sharpening threshold. So so for the to perform on usually we set 100%. For example, for the edge contrast.
you. Second, radius is you can set before to 1. So regularly we set about control the edge width. Of the edge width. Your result say, I'm going to so the range you are going to magnify your hypothesis condition. So when set up small in spatial holding, so it's even small difference in testing, you are going to hypothesis. So this will more sharpening. Small. So they are talking about what's the difference range. You are going to magnify, hypothesis your component. If you set a very small, which means even the background, they only have very small difference, you are going to hypothesis the result. So if you set a small, it's a more sharpening. If you set it large, only small, less, not much, less sharpening. Okay, so these three parameters, you are going to use a sharp mask from the Photoshop and get a very good result. But I say, you only have a positive, negative subtraction. Okay, we say subtraction because we are going to have the high pass component. And then add back part of your original image. That's the idea. Idea for sharpness. So let's see. Is that okay? Restate and sharp mask. For image, high pass component. Add back to original image. That's it. So, but Photoshop get a very good suggestion, and including all these different parameters. So is how to sharpen with a sharp mask. It's a Photoshop menu, and they are going to combine the structure. So they have to suggest some. Let's go back to look at it. I will give you this link on the information for them. Okay. When you have to look at this image and check out the focus on. Okay. So see, you are choosing a sharp mask, and then see, we just three different. Enhance higher, your contrast will be higher. What the rate is okay, and the threshold of the hypothesis. So if you choose this small, we can see very different result for you to see. Okay, actually, okay, I break the radius. I remember how come here. Actually, every step they have some
Okay, they will give you some result, actually. I don't know, you never, you go back and as a network open Photoshop essentials.com. Anyway, yeah, that's fine. That's fine. Yeah, we are not going to spend time on here. So they'll give you different selection on these three parameters. You will see a difference. If you set up to big edge width, high contrast, even the threshold is set up very small threshold holding, which means even the background, the common background, you are going to enhance, it becomes very ugly. So it's become a nature, I should say, a nature, not ugly. Okay. So it's depends on how you use it. Okay. So please take time to read their manual profile and see how to design and some mess in your homework read. Okay. Yeah, here is some high boost filter. And other component depend on how you can use two, but the result become only a component, right? So A will be one is a good choice here. A become one will be good choice. Originally made. So A should be larger than 4. Okay, M file you are going to design is an unsharp high boost. Okay. Okay, so if you look the first technique is intense. We have and you have all different processes. So inside -4, your original image is going to minus this operator, right? If your process is a positive in the center, positive A or -1 in the outside. So you are going to add up this image, this filter. A is plus this one. Sometimes A should minus this one. It depends on your process or filter at the center. Okay, so it's a compute like this one. It's A equal to 0, A equal to 0. So only what? Only quarter left. So it's not good as you want. So what can we do? First thing, in has using the math in this equation use A equal to 1. So add back this one. Actually this one. Add back this one. So do you think it's good? If it's a favor, done. A to 1.7. So you will enhance the part of your image component. So can you compare? So A is the final way to adjust. I think our M file, you have to input A for your parameter. Okay? So if equal to 1. Okay, see? Clear, right? You look at original line. It's but you combine. So the scale here is much bigger, and highlight or see, and we try to tend to enhance the image. So it's a different. In calculus, right? The gradient, T2 in Chinese, we call it T2. So how you do that one? The T2, the gradient, you just take the first order derivative, right? Okay, so this is the first order derivative. Sometimes we write this one in x direction, in y direction, and it is a vector because the gradient has the directional content. So in x direction, in y direction. So in the 2D image, you can tell me at this spot, this pixel, you can tell me where is the largest gradient direction. Okay, sometimes it's go to horizontal, sometimes vertical, sometimes it's a diagonal direction. So we can tell you the magnitude of the gradient and the direction of the gradient. So there are two values you have to calculate. The first one is the magnitude of the gradient. So every pixel in your image, you can find out the gradient at this point, at this pixel. So you have to calculate and use this gradient operator. And then also you can calculate the direction. So how can you calculate? The direction is for the mathematics, the gradient direction is a tangent of the wrong f wrong y, wrong f wrong x. So depend on your y direction divided by your x direction, the ratio, and then take hyperbolic or tangent. So the gradient is equal to this one. The gradient, the magnitude equal to this one. Direction is equal to this one. So you know which the direction in this pixel, the gradient is largest. Okay, so if this is the vertical platform step function, the direction must be 0 degree because from left to right hand side, from 255 to 0. So it immediately the direction will be 0 degree. Anyway, so how we approach the gradient in your mask representation, then apply on your image. So it's approximation to the magnitude of the gradient is normally used to consider the following image. So now we have used 3 by 3. And you are going to look at this center pixel 0.5 and then see how it's gradient the result. Okay, so how can we do? The easier way is we can use the approximation postulate. 0.5 minus 0.8. We call it the direction in y. And then minus here. Okay, it's y direction. And also this is for horizontal is 1 here minus 1 here. So for this direction, so it called Prewitt direction. So we have a 2 direction mask, one dimension, one order derivative. This is your pixel here. Just take one step difference in x direction and y direction. And then you can sum up their square result, difference result, because gradient. So it's a gradient, how the differences. You can represent by this gradient value. And we can use this 0.5 minus 0.9. Okay, so this is for horizontal, vertical. Sometimes we can have a diagonal and the other diagonal direction. So it's become like this. Okay, 0.5 minus 0.9. This minus 0.9. So it's minus 45 degree gradient different. And also 0.6 minus 0.8. So this one minus this one. So at this point, we have two different direction, diagonal direction. You use this operator called Robert cross gradient. Gregory, Robert, so all different names, but they published in maybe 40 years ago, so you don't have a chance to publish your name by this gradient filter. So it's very straightforward. I just look at the different direction, the gradient in different direction, and this is called Robert cross gradient operator. Especially look at the diagonal result. Okay, so very straightforward. Just multiply this coefficient on this location. Your center. Just look at the neighboring pixel and take the differences, and then try to take the square of it and take the root of the square summation. That's the result. Okay. So Robert cross gradient operator. Use this one. Robert cross gradient operator. See the original paper image and this one in vertical, horizontal, you get this result. Right? Take the cross gradient operator, you get this result. They have some minor differences. The mask pair you use. The most popular we call it a software operator. Okay, software operator, and Prewitt operator. So what's like this shape? So also and vertical direction, but they use and use coefficient. Calculate this one. Calculate this one. Neighboring pixel. Okay. H1 is for horizontal. This one is for vertical. But this is center pixel. So neighboring pixel to calculate their differences, but with different coefficients. Then specific name there. This is software operator. Okay. The magnitude on the result. Prewitt is use this coefficient. So there is, but you can see the summation of the coefficient is 0. Okay, so okay. Result of the image. So it's all Laplacian operator here. Yeah, I think there's
Okay, let's example for this one. Let me do this one first. Because we are host for a university. So let's conclude today's work for this one. Okay, this again the short mesh. If you use profile to look at this one, and this original image distribution of profile, right? And the second is the blur image, right? So you can see actually for the edge part, this is smooth, right? So original, and then you use a blur image. Blur image just smooth your edge. So it's smooth from the blue line. Okay, the top line is original. And then unsharp, what's the unsharp mesh? Remember? G mesh. This one minus this one, right? So original image minus your low-pass image. This result. So immediately see the difference here. So this notation method minus value, and this rotation method positive very rare. And remember, unsharp is add back your partial weighted. So original image here, this is the final unsharp image signal, right? So what's the result? You have original image, but at the edge order, a little bit enhanced. Make your image more highly contrast. The detail, the fine detail will become more clear. So that's the result in the true image here. Again, blur image of the north pole of the moon, and then the B is the Laplacian, and then use this one. This is a high pass only, so actually it's like a G mesh, and then add back your original to this one. So maybe you cannot compare from this image and the middle of the right. So look at your textbook very clearly. This is the original high pass result, add back all of it. So compare these two. So it's more clear. Small one here you enhance larger. So the edge component. Which one to be more clear, right? So this is your homework 3. So please, I think Tia will give you some test image, right? Try to do that one. Okay. So our class dismissed here. If you have a question, come here. Okay. Okay. 哎，韩静，拜托帮我收。好，我要赶去。